Hello, and today I'm going to be talking about kinematic calculations and how you can use acceleration in them. And this is very important because it's not just something that you're going to need to know for the rest of this unit or the rest of this physics class, but in all of your future physics classes that you end up taking. So before we get too far into that, I figured that I would talk about what we know up to this point. The slope of a position graph gives you the velocity. So above my head, you can see the position graph and the velocity graph, and how as the slope of that position graph goes up, so does the velocity. And this makes perfect sense because the very definition of velocity is the change in position over time, and the slope of that graph is the change in the y-axis over the change in the x-axis, or the change in position over time. Similarly, the slope of a velocity versus time graph gives you the acceleration. So here we see the acceleration graph, and we can see that it is always equal to the slope of the velocity graph. Again, this makes sense because the very definition of acceleration is the change in velocity over time. Also, the area of a velocity versus time graph gives you the displacement. So if we were to take the area of any part of that graph, for instance this one that I have highlighted here, it's going to give us the displacement of our object up until that point. And since we started that at 0, that's also then going to give us a position. The same thing is true with the acceleration graph. If we were to take the area underneath that acceleration graph, like what I've got highlighted here, that's going to give us the change in velocity, and since we started out with a velocity of 0, it is going to give us what our velocity is. Keep in mind that you can have negative areas if you are going underneath that x-axis. We also have two equations. We have our displacement equation, so that's displacement equals 1/2 times the acceleration times time squared plus the initial velocity times time. And that works out really nicely because if you notice in our previous video, acceleration was always 0. So if you take out that 1/2 at squared, because acceleration would be 0, you have the equation that we were using in the last video. Now this is a very important bit. That only worked because the acceleration in those problems was 0. If you have a problem where there is acceleration going on, you have to use this full equation with that acceleration term in there. We also have another kinematic equation. This is sometimes called the time-independent kinematic equation because, well, time isn't in there. It's velocity final squared equals velocity initial squared plus 2 times the acceleration times the displacement. Now you might also be noticing that all of these have vector arrows, and that is because the acceleration, just like velocity, just like displacement, is a vector. So when something has when an acceleration in the same direction as its velocity, it's going to be getting faster and faster. If something has an acceleration in the opposite direction of its velocity, then it's going to be getting slower and slower. So again, that direction really matters. In fact, in physics, we almost never use the term deceleration because that in everybody's mind means slowing down. But acceleration is a vector, so we want to just make sure that we are communicating the sign of our vector and then whether or not we're speeding up and slowing down on whether those signs agree or whether those signs don't. So let's talk about motion maps. We talked about this last time when we had constant velocity problems. Same thing is going on here. It's just now we're adding an extra bit. A dot will still represent the position at each time interval. An arrow coming out of that dot is still going to represent the velocity, but now that we have acceleration, we're going to add an additional arrow sitting right next to the dot that is going to represent how much acceleration there is and what direction that is. So let's do an example with this. It is a myth, unfortunately, that Galileo climbed the Leaning Tower of Pisa with 2 cannonballs in order to demonstrate that a mass doesn't matter when you are dropping any objects. However, let's not let reality get in the way of a good story. So let's go ahead and use that as an example problem. So the Tower of Pisa is 56.7 meters tall. So if Galileo were to drop those cannonballs from the top, how long would it take for them to hit the ground? And graphs and motion maps and show your work, all of the details that physics teachers love to throw into problems to make you do more work. So let's go ahead and get started. So the equation that we're going to use in order to figure out how long it's going to take, how much time it's going to take, is our displacement equation. So displacement equals 1/2 the acceleration times time squared plus v naught t. There's just one problem. Unfortunately, there seems to be way too many unknowns in that equation than what we can deal with. Or are there? So the acceleration due to gravity on Earth is a constant. It is 9.8 meters per second squared. Now, some of you might be going, how on earth is there a square second? Don't worry, this gave the 4th grader version of me no end of difficulty trying to puzzle it out. But it basically works down to be just an abbreviation of math. So acceleration is defined as the change in velocity over time. Well, the units for velocity is meters per second. So if we put the units in there, we see that it's meters per second. And that is a really good way to think about it. It's the rate that the velocity is changing. It's the rate that the meter per second is changing every second. Unfortunately, that doesn't trip off the tongue very prettily. So we can do a little bit more math here. So let's go ahead and say that, hey, whenever we're dividing, like that right up above here, that's the same as multiplying by the reciprocal. So meters per second times 1/seconds. And you can see now that, hey, that's going to equal meters per second squared. Now, because acceleration of gravity on Earth is always that negative 9.8 meters per second squared, it's sometimes, well, commonly abbreviated as g. And, well, because Earth is the only planet with cannonballs, we can usually assume that physics problems are going to be taking place on Earth, and therefore we can just go ahead and use g, that negative 9.8 meters per second squared. Why did I say negative? Because of course we are going to be going down. So, initial speed when dropping an object. That is just going to be 0. Whenever an object is dropped as opposed to thrown, the initial speed is always going to be 0. And we can demonstrate with that with this golf ball right here, because if I drop it and try to catch it immediately, you can see that I can actually do that because it hasn't had time to speed up, so I can actually catch it. Now, if however I were to wait a moment, you can see that I miss and have to catch it on the rebound. So now that we know both of those things, maybe we can use that equation to a little bit better benefit to ourselves. So d equals 1/2 at squared plus v naught t. Well, v naught, that's just 0, so we can get rid of that. We're trying to figure out how much time it's going to take to hit the ground. So we can go ahead and solve for time. So as doing that, we get time equals the square root of 2 times the displacement over the acceleration. We need to be a little bit careful about our signs here because remember, these are all vectors, which means direction matters. So when we plug in our displacement, we are going down 56.7 meters, which means our displacement is going to be a negative 56.7. And the acceleration again is down, which means that it's going to be a negative 9.8 meters per second squared. And we can then do that math and find that it's 3.4 seconds, which is the time that it's going to take to hit the ground. Now, in order to figure out how fast it's going to be hitting the ground, we can use the velocity equation for that one. So velocity equals acceleration times time plus the initial velocity. And again, that initial velocity, because we're dropping the object as opposed to throwing it, is going to be 0. So Negative 9.8 times 3.4 seconds plus 0 because we're dropping it, and we get an answer of 33.3 meters per second. So now let's take a moment to do the graphs and the motion map. So let's start with the motion map. You can see that I modified that equation over there a little bit. Rather than displacement, I went ahead and broke that up into its initial component and its final component. And also, instead of dealing with x, I'm dealing with y because we're going up and down. So at time equals 0, well, time squared is going to be 0. Velocity initial, well, that's still 0, times time, that's still 0. So the only thing that matters is our initial position, and that is going to be that 56.7 meters, so that's why there's a dot all the way up there. Velocity at this point, it's still going to be 0 because we just dropped it. So there is no velocity arrow, but we do have that negative 9.8 meters per second squared acceleration. So that's why I have the purple arrow sitting right next to that green dot. 1 second later, we have now traveled about 4.8 meters. So we are sitting at 50 meters, but now we've started picking up speed. We have now accelerated for a full second. So our velocity is going to be negative 9.8 meters per second. So I have a velocity arrow sitting there, and our acceleration is that same negative 9.8 meters per second squared. Fast forward another second, now we're at about 36 meters. We have now doubled our velocity because now we've been accelerating for 2 whole seconds, so we have twice the size of the arrow, but our acceleration again remains exactly the same at negative 9.8. Fast forward to our third second, we are now at about 11 meters. We have now been accelerating for 3 whole seconds, so we're going to be at 29.4 meters per second going down. Big red arrow. Again, same acceleration. 4 seconds. Well, now we've already hit the ground, so we'll just be sitting there at ground level. No velocity, we're stuck in the mud. No acceleration, we're stuck in the mud. So, when looking at the kinematics graphs for this, we're going to be a constant negative 9.8 meters per second squared for acceleration. For our velocity graph, we know that we're going to be starting off with a velocity of 0, and it's going to have that slope of negative 9.8. So the velocity graph is going to be a straight line just like that. For our position graph, we could plot the points that we have over on the motion map, or we can just go, hey look, we know we're starting at that 56.7 meter point, and we're going to start with a slope of 0 that's going to get steeper and steeper and steeper in the negative direction. So it's going to look something like that. Did we need to know the mass of the cannonballs? And the answer to that is quite simply no, because one of the things that Galileo demonstrated in this very experiment is that mass doesn't matter. Now, here on Earth, we are always looking at light things falling slower than heavy things, but that is just because of air resistance. And when you take air resistance out of the picture, a hammer falls just as fast as a feather does. As you can see, when we went to the moon, that is exactly what happened.
Well, in my left hand I have a feather, in my right hand a hammer. So I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 up here, and hopefully they'll hit the ground at the same time. How about that?
So that final part of the Apollo 15 mission was great for physics teachers, because not only does it demonstrate that very point that we've been trying to get across, you can also then time exactly how long it takes for that feather to drop, and then calculate what the acceleration of the moon on the moon is. Now, some of you might be going, that's cheating, you went to space. We can do the same thing here on Earth, and that is exactly what Brian Cox did in this documentary about gravity. He took a bowling ball and feathers and put them in the biggest vacuum chamber here on Earth and let them drop. So right now what's going on is it's in slow motion just to prove that, hey, they're falling at exactly the same rate. And they are dropping a very large distance because this was taken in that vacuum chamber that NASA uses to test space systems like rockets and things like that in a vacuum. And you can see that those fall at exactly the same rate and they hit at exactly the same time. So let's do another example. In this example, we have an angry physicist hurling a boulder straight up, and it leaves the thrower's hands at 39.2 meters per second, which is essentially 90 miles an hour. And we want to determine the maximum height of the boulder, the total time that the boulder is in the air, and we're going to have the physicist catch it on the way down. Now, what kind of a physicist can actually throw a boulder at 90 meters per second straight up in the air? And the answer to that would be none other than the Hulk, because of course Bruce Banner is a high-energy physicist. So, in order to figure out how far we can throw that boulder up, and we sort of figuratively here, we can use this equation, the time-independent kinematic equation. Because when I throw the golf ball up in the air, you notice that when it gets up to the top, it stops for the briefest of moments. The velocity is 0 right at the arc. So that means that the final velocity is going to be 0. So we can get rid of that. Now we just need to solve for displacement. Displacement is going to be equal to negative v initial squared divided by 2 times the acceleration. And we can look at this and go, all right, so our initial velocity, that was a positive 39.2 meters per second. We square that, we divide by 2 times the acceleration, which of course is negative because the acceleration due to gravity is going down, and we get our height as being 78.4 meters up in the air. This is a very good thing when your name is Bruce Banner and you need to protect the Earth from invading aliens summoned by the god Loki. So we also wanted to determine the time that it's up in the air for. So what we can do is take this d equals 1/2 at squared plus v naught t equation and solve for t. Now when I toss the golf ball up in the air, the displacement between when I have thrown it and when I have caught it is 0 because I am throwing it and catching it at that same location. So we can take that displacement, make the displacement go to 0, solve for time, and one of the really nice things about this when displacement is 0 or initial velocity is 0 is that gives us a term that goes away so we don't have to end up solving a nasty quadratic. So continuing to solve for time, we get negative 2 times the initial velocity divided by the acceleration, which again is going to be 2 times 39.2 divided by that negative acceleration. The negatives are going to end up canceling, so we're going to get a total time of 8 seconds. What does this look like graphically? Well, pretty much it's going to look really similar to our Galileo problem. The acceleration is going to be that constant 9.8 meter, negative 9.8 meters per second squared. Our velocity is going to have that same slope, but now just because we're starting at 39.2 meters per second rather than 0, it's going to be a little bit more positive. And then for our position graph, it's going to look like it's going up and then back down, because it essentially is. Now, if you were to go and take this point right here and only keep the right-hand parts of those graphs, you would get exactly what we saw in that Galilean graph. All right, so motion map. We're going to be starting at 0, and and then moving up at nearly 40 meters per second, so that's going to get a very large red arrow, and that negative 9.8 meters per second squared acceleration arrow. And we can keep going. 1 second later, we're about at 35 meters. A second later after that, we can see that we're still slowing down, but moving up, and that acceleration arrow stays the same all the time. Then we're getting almost close to the top after 3 seconds. We can see that our velocity is now much slower. It's only now 9.8 meters per second, but we still have that same acceleration. When we're at the top, we are perfectly stopped. At the top of all of those arcs, the velocity in the direction up and down is going to be 0. And still, the acceleration is a negative 9.8 meters per second squared. It doesn't change direction, it doesn't change value, it is always going to be going straight down, just because gravity is always pulling us straight down. 1 second later, we are now moving down at 9.8 meters per second. And again, same acceleration. Now, this is kind of nice because our graphs and our motion maps are going to be symmetrical with time. It's going to be the same time going up as it takes coming down. We're now at 6 seconds. We're now coming down at 19.6 meters per second. We're now at 29.4 meters per second, and we are now back down where the Hulk can catch his boulder, and well, now because he's caught it, it stopped, and we are done. Hopefully you found that helpful. I'm going to put a link to the full video where Brian Cox is dropping the bowling ball and the feathers in the description, and I hope you have a wonderful day.